This lecture has grown, and I think we started off, this will be the 6th of the series, annual lectures. The first one was held in the Crowell Hall, the circular Jenkins room, and it turned out the very first one, the people were too deep around the circumference, standing too deep around the circumference of the thing. I was one of the ones standing. And it turns out that we knew immediately we had to change venue. So we switched and went to the Cal IT Square Auditorium. And the first one that we had there was quite comfortable. You know, the seats there were vacant seats, and it wasn't crowded, and you weren't crunched up against your neighbor. And so that worked pretty well. But for the next two, it grew and grew to where last year the report, well, I didn't make the one last year, but the report to me was that it was standing room only, and there wasn't enough food. And the reason for that apparently was the fact that the standers ate the snacks and helped themselves while the lecture was going on. So it's grown immensely, and I think that we're going to try to stick with this venue. It's a very nice auditorium. We all know that. It can handle more people, and it's going to be, I think, a real thing to look forward to in the future. One thing I wanted to point out, too, is that all of the previous lectures are on the department website. You go to the ESS website and go to Reberg Lecture Archive, and the previous lectures are there. And if you want to see that, or if you want to check this or pass the information on to a friend, feel free to do so. This wanted to say too that the terminal disease that afflicted Carolyn and eventually took her from us last October was the kind of a thing that, well, like I say, I think that this lecture series is a really fitting tribute to her curiosity, her love of learning, and her basically general attitude. And I think that she would be very happy to be part of this, have her name on the list, the first name on the title of the lecture. So with that, I'm going to call Kathleen to introduce the speaker.
Hi, everyone. So it's my honor to introduce this year's Carolyn and William Reberg Endowed Earth System Science Lecturer. This lecture is traditionally selected each year by 2 research groups in the Earth System Science Department. And this year, the honor fell to Eric Saltzman's group and my own. And we actually put quite a lot of thought into this process, and we met a couple of times together with all of our students and researchers, and we decided 100% democratically who to invite. And so I'm very pleased to introduce Ed Brook, who we selected to be this year's lecturer. Ed's research combines fieldwork in polar regions with very detailed and difficult analytical work in the laboratory to investigate the history of greenhouse gases and climate utilizing ice cores. So this is very much in line with the Saltzman Group research. His work also, though, involves detailed comparisons with precisely dated paleoclimate records from around the planet, including notably those from low latitude and monsoonal regions, where my group does a lot of research using speleothems. And these regions are especially important given the important role of tropical wetlands in atmospheric methane variability, which we'll probably hear a little bit about today. And of course, this topic is also highly fitting for the Reberg lecture because given the huge impact that Bill's work has had on our understanding of global methane biogeochemistry. So without further ado, I'd like to introduce Ed Brook. Ed is currently a professor in the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University. He was recently named a distinguished professor in that university, which is a select honor reserved for only a few people. He's also received many other honors in his life, including being a few years back elected as a fellow of the American Geophysical Union. He did his undergraduate and master's degrees in geology at Duke University and the University of Montana, respectively. And then he did his PhD in chemical oceanography in the MIT Woods Hole Oceanographic Institution. So just one final word of thanks to Bill Reberg and to Carolyn Reberg for enabling us to do this lecture. And without further ado, I'd like to introduce Ed Brook to give the lecture. Thank you.
Thanks very much for the introduction and for the invitation. It's a real pleasure to be here, and it's really a pleasure to give a lecture named for Carolyn and Bill. I've known Bill for quite some time. I'm very sorry that Carolyn is not here to have those conversations afterwards. But nonetheless, it's great to be here. Every time I come here, I learn a lot. This is a fantastic department. I think I got my PhD 25 years ago, so I couldn't have come here to study. But and Woods Hole was okay, but it would have been fun to come here too. So what I would like to do today is kind of give a broad discussion of some of the things we've learned about the history of greenhouse gases and climate from ice cores, sort of focusing on results that have come forward over the last 10 years or so. Try to sort of keep it at a relatively basic level, hopefully touch on some new things that people will be interested in, throw in a few of the more technical details now and then to keep Eric awake. Or some other people, and hopefully you'll get a sense of some of the things we're doing. And I'll talk mostly about carbon dioxide and then talk in the beginning and then do some methane stuff near the end. So to start with, a lot of people show pictures of their lab group when they first, at the beginning of the talk. This is not my lab group. This is most of the scientists who study ice cores in the world at a conference in 2016. And I'm just showing this photograph to remind myself to say that we, like many people, work on sort of big projects that take many people to accomplish. There are data in this talk from projects from all over the world. Can't thank all the folks, but I just wanted to emphasize the point that this is a scientific community. Not all scientific communities are friendly. This one actually is a very friendly scientific community, and part of the reason I enjoy working in there. And you could pick out your favorite ice core scientist if you look closely. So just an overview of what I'd like to talk about. First of all, just a little bit of the basics about why we can get air out of ice, how that works. And then we'll take sort of the long view, talk about the long records of greenhouse gases that cover 800,000 years. Talk about one of the sort of vexing problems in this field that gets into the news now and then when we think about the reality of climate change that has to do with the timing of temperature and CO2 change, something we've studied recently. And then say just a little bit about some of the puzzles and challenges that have come up with in this work. And then I say a little bit about a new project that actually looks at older ice. And then we'll move on to talk about some of the things that Kathleen sort of alluded to, some rapid changes in methane and CO2 and what might be causing them and what implications they have for what might be happening in the future. So that's where we're going. I may have to flip through a few things quickly to make it on time, but we'll see how it happens. Just to start with, to set the stage, something a lot of people in this room know a lot about, the increase in atmospheric carbon dioxide in the modern atmosphere measured at Mauna Loa, the Keeling curve, and then also shown here in green, measurements of atmospheric methane, also rising rapidly. And both of these curves also have had input from people here, I believe. The point of showing this is not to prove to you that CO2 and methane are rising. I think most people understand that, but to say that the direct measurements of these gases in the atmosphere in a systematic way only go back to really the late 1950s. And to understand the atmosphere before this, while there are scattered measurements for earlier times, we really have to go to the ice archive to get a detailed picture of how the atmosphere evolved. It turns out that around the time that Keeling was beginning this measurement program was the same time that people started thinking about the ice as a way of understanding the atmosphere. And so this gentleman, Per Scholander, who worked at a number of places, including Scripps Institution of Oceanography, thought about gases and ice in the 1950s and recognized that it is possible that ice would preserve a record of the atmosphere. And they actually got on a boat and went out and collected icebergs in the Labrador Sea and measured gases in the ice. And they couldn't measure trace gases at the time, really. But this is a table from that paper. And the point of the table was that the oxygen that they measured when they extracted the air was about the right number, around 20%. And he points out in this paper that this indicates that air was being trapped by the compaction of snow on Greenland, and then the ice eventually flowed into the ocean. And I think this is maybe not the first, but one of the first suggestions that there might be a record of ancient air and ice. Scholander went on to study the diffusion of gases and ice and sort of really set the stage for the fact that we might be able to study this process. So this leads us to sort of how this works in our modern research setting. The left-hand photograph is this ice core drilling site at the South Pole. Several people here at UCI are involved in this project. Just to sort of give you a picture of what the surface of the snow is like. The right-hand side is a diagram of the firn, the unconsolidated snowpack at the upper parts of the ice sheets. And it's just a diagram to illustrate the fact that air diffuses through the snowpack, and the snowpack gradually densifies. It compacts by the sliding of snow grains against each other and the recrystallization of snow grains, and ultimately traps the air as bubbles, and that's why we have a record of ancient air. This also creates a problem related to the age of the air with respect to the age of the ice, which I'll come back to later. So starting in the 1960s, various research groups around the world started drilling ice cores, both in Greenland and Antarctica. The major deep ice cores are shown on this map. There are cores in various places for various reasons, primarily because at different sites the snowfall rate is different, and therefore both the detail that you can get from the records and the ultimate age of the records are different in different places. And typically we want to go to places where the accumulation is relatively simple, where the ice flow is relatively simple, and we can easily interpret the stratigraphy as we go downward. I'm not going to say too much about ice core age scales in this talk, but we have a variety of ways of doing that. Like many kinds of science, there are lots of technical challenges for collecting ice cores. This is a photograph of the American, one of the American ice core drills lying on its side. It's a sort of specialized engineering device. You can't go out and buy one. This is turned vertical, and I'll show you a movie of that in a minute to actually operate it. You can see a core at the bottom. And of course, we have to worry a lot about getting the ice back to the United States and safely and not melting it, and then ultimately storing it. This is the National Ice Core Laboratory in Denver. And I just show this photograph to make the point that these kinds of archives are extremely important. That all of the American ice core collection is here in Denver. There are cores from the 1960s there that, in fact, my most cited paper comes from measurements we made on a core collected in 1967. So the support of archives like this is absolutely critical. And there's a story about this right now. The cost of this archive is going up, apparently, because the cost of warehouse space in Denver is increasing, and that's because of the marijuana industry. So, you know, things are interesting sometimes. Here, I'm just going to show you a very short snippet of a movie that was actually entered into the McMurdo Station Film Festival. Some of you may have seen this. And what this person did is attach a camera to the top of the drill. So you're going to see the ice core drill lying on its side, and it's going to tip up, and it's going to go down into the hole, and you'll see it hanging on its cable. It's a motorized device, and so when it gets to the bottom, it turns and drills into the ice, and then they pull it back up and bring the samples to the surface. And you have to do that over and over and over again because you're going down 3,000 or plus meters in some cases. So there's music to this, but I thought not serious enough for this audience. Anyway, so that's sort of the technology. There's quite a bit involved, and of course, this is way out in the middle of Antarctica, so you know, we're quite grateful to the funding agencies for being able to do that. Of course, then when we get home, we have all kinds of laboratory things to do. We spend a lot of my time in my laboratory building instrumentation for measuring gases, and in particular, trying to get the air out of the ice without contaminating it, similar to the work that Eric Saltzman's group does here. We don't have to talk about all the details, but the point is just that a lot of what we do takes quite a bit of time, and we spend a lot of time doing plumbing. Well, we're going to start talking about results from the ice cores by talking about the modern atmosphere. Again, something that's fairly well known, but worth reviewing. These are 3 panels showing the CO2, methane, and nitrous oxide concentration of the atmosphere going back to about 1700, so the start of the Industrial Revolution. And all 3 of these gases start to rise at about the same time. And the blue line on the plot is the modern atmospheric record. You can see that it trends very nicely into the ice core record. These are data from Antarctica, actually. And one of the things we've learned from studying the ice core record is really how anomalous the current situation is. Modern growth rate of CO2, for example, the most important of the 3 greenhouse gases shown here, is about 10 times faster than anything we've measured in the pre-industrial period. For methane, it's also true that the growth rate is quite a bit faster than most of the changes we see in the ice core record. There actually are some times, which I'll get to later, where we see some natural variability that comes close to some of what we've measured in the last several decades. So that's kind of interesting. And so these kinds of data have been replicated many times, many places, quite solid. But the ice is where we get this information about the onset of the Industrial Revolution. Sometimes people ask, why, how do you know this is due to humans? Maybe not necessary for this audience, but there are pretty clear, stable isotope fingerprints of human activities in these data. So this is the CO2 concentration rising, 2 different ice core records here, where it's in orange. I'm referring to some data from my lab. OSU's colors are orange and black, so just that's why. This is the carbon-13, carbon-12 ratio, which is taking a deep dive towards negative values as the CO2 starts to rise, a clear signature of fossil fuel burning. Something that, in the methane and nitrous oxide isotope records, there are similar fingerprints that make it very, very clear that we're seeing fossil fuel changes. And of course, that's not really a mystery, but it's sometimes useful to remember that we do have that evidence. So this is a short record, and we can switch gears completely to a much longer time frame. So now we're at 800,000 years ago to present. Then the very end is cut off here. And this is from Antarctica, and most of the data shown here are from a European project called EPICA and the Dome Sea ice core, which is the longest continuous record we have. And sorry about all the wiggly lines on here, but I'll try not to show too many plots like this, but this is the carbon dioxide, nitrous oxide, and methane concentration history over this time period. I'm also showing what is the deuterium to hydrogen ratio in the ice core, which you can think of simply as a proxy for temperature. And down at the bottom, another isotopic record. This is from the ocean, and this is the isotopic composition of calcium carbonate organisms in the deep ocean, which is a proxy for ice volume. So in all cases, warm conditions or interglacial conditions are up on this slide. This is the dust flux to Antarctica from the ice core. The scale is reversed here, so there's less dust during warm periods and more during cold periods. And the main thing I wanted to do here is to show those of you who are not familiar with these data sort of how closely coupled the temperature proxy is with the greenhouse gas variations. For those of you interested in nitrous oxide, the reasons there are gaps in here is that in the dusty ice, there's actually production of nitrous oxide, probably from microbes, and we've cut out the dusty portions of the record. So it's very clear that warm conditions correspond to higher levels of greenhouse gases and cold conditions, lower levels. And it's also very clear that the modern atmosphere is very different compared to these records. So that arrow shows where we are today at 400 parts per million CO2 relative to the ice core record. That arrow shows where we are at about 1,800 ppb for methane relative to the ice core record. And so clearly the modern atmosphere is anomalous over this relative to this time scale. That's not a surprising result now either, but important to remember. So this coupling of temperature and greenhouse gases is sort of a fundamental property of the record. The temperature changes themselves, which I'm now plotting here on the bottom of this plot, sorry about that, I'm putting methane and CO2 here, are ultimately driven by variations in the Earth's orbit, which affect the patterns of solar radiation impacting the Earth. So we're talking about the Earth's tilt and the Earth's shape of the Earth's axis and the direction that the spin axis points. And those things impact the climate system. And the way we sort of think about the role of greenhouse gases in the system is as a feedback. Orbital variations impact solar radiation, which in a variety of ways impact climate, impact the entire Earth system, and ultimately impact the phenomenon that control greenhouse gases in the atmosphere. And then, of course, these things feed back on each other. And most of the analysis of the relationship between global temperature and greenhouse gases on this time scale suggests that about roughly 40 to 50% of the temperature changes are due to that feedback. That's the sort of standard thinking. The mechanisms that control these gases and why they behave in that way are obviously a major research area, and we certainly don't know everything about that. Carbon dioxide cycling is dominantly believed to be due to changes in storage of carbon in the ocean, although land processes are also involved. Methane cycling is dominantly believed to be due to changes in terrestrial processes, primarily the emission of methane from wetlands, although there are a number of other sources that may be important, and we'll talk a little bit about how sources might be varying on these some of these timescales in a few minutes. So that sort of sets the stage. And what I'd like to do is talk a little bit about the work that we've done on two of the problems related to these sort of long-term cycles. And one of the problems is fairly simple to get at, and that is the timing of carbon dioxide and methane change with respect to temperature. There's been a lot of sort of discussion, both in scientific literature and sort of leaking out into the popular media about this chicken and egg problem, CO2 change before or after temperature on these sort of, as you go from an ice age to a warm period, and what does that mean? Does it invalidate that greenhouse gases are important for climate? You hear things like that. And then I'll also just say a little bit about mechanisms of carbon dioxide change. And this is a much harder problem that lots and lots of people work on. Just say a few things about that. And to do that, I'm going to introduce two different sort of newer archives of ice. One is something called the Waste Divide Ice Core in West Antarctica, a project that finished relatively recently and provided some new windows on on some of these problems. And I'm going to talk about a fun project that we're working on with a number of colleagues on a glacier in Antarctica where we can get old ice at the surface. And so we'll start off by talking about the Waste Divide project. This is in West Antarctica. WASTE stands for West Antarctic Ice Sheet. Divide is at the ice divide where ice is flowing off in several directions. The ice core is located here. The reason to go here was that the snowfall rate is quite high. And most Antarctic ice cores have relatively low snowfall rates. And that the reason that's a problem has to do with this gas trapping in the ice. So we talked about this firn layer and the fact that bubbles are trapped here. Well, the air diffuses through the snowpack relatively quickly on timescales of about a decade. So air trapped at the base of the firn here is actually quite a bit younger than the ice that surrounds it. And that age difference can be very, very old. This is a graph from 70,000 years ago to zero of this age difference. It's called delta age for a variety of different ice cores. The ones up here are all from places where the snowfall rates are very low. And you can see that these numbers go from about 2,000 years up to about 4,000 or even 5,000 years. Those numbers are big and they're uncertain, and that creates an uncertainty when we want to understand the age of changes in the gas phase relative to something that is in the ice that we're interested in, for example, isotopes that tell us about temperature change. So Antarctica is the place we want to go if we want to reconstruct carbon dioxide levels because the ice is clean. But if we want to answer the chicken and egg problem, we need to be down in here where we have high snowfall rates and relatively low values of the parameter delta H so that we can get a more accurate understanding of timing. So that's why we went to this site. And, whoops, wrong direction. The diagram on the right is a summary of what we found. This is from data from a paper by Sean Marcotte, who was a postdoc in my group. The diagram comes from a summary article that's in Press and Nature. And what it shows is carbon dioxide change from the Waste Divide ice core, as well as a composite record of temperature change in Antarctica. This is actually the anomaly in the Antarctic 18 oxygen to 16 oxygen ratio, but you can think of the pattern as a pattern of temperature change. And if you look closely, starting at about 1,000 years ago, this is the end of the ice age, CO2 starts to rise, and it actually has several fits and starts. It doesn't rise monotonically. And you can also see, if you look closely, that the timing of temperature change in Antarctica actually matches the timing of CO2 change. It's very difficult to discern a lead or a lag between these two variables. This is important because previous work had suggested that carbon dioxide change actually lagged behind Antarctic temperature change by about 800 years. And those data were from one of these cores where the gas age, ice age difference is very big, and it was just difficult to constrain properly. They would agree with us now that this very, very synchronous behavior is really the right answer. So Antarctic temperature and carbon dioxide are essentially changing at the same time. Now, you might ask, well, okay, what does that actually mean? Maybe it tells us something about the greenhouse effect, but we're really interested in the global temperature if we want to be thinking about how global change works. And global temperatures are harder to reconstruct, but the best sort of average reconstruction of global temperature by going all over the world and collecting all of the possible temperature indicators that could be obtained. Jeremy Shakin in 2012 created this curve. And when you compare these, and it's fair to make the comparison, actually CO2 starts to rise, it rises a little bit faster than global temperature. There's a little bit of a lead of CO2 over global temperature. And that makes a lot of sense, and the system seems to be working the way we think it should. Why are Antarctic temperature and carbon dioxide coupled so tightly? That probably has something to to do with more specific dynamics of the carbon cycle and ocean circulation. The sort of dominant thinking these days is that the ventilation of the deep ocean around Antarctica and changes in biological activity in the ocean around Antarctica are probably the reason why these things seem to be so coupled together. And there's lots and lots of people trying to understand the details of that problem. Methane is hanging out up here waiting for us to talk about it, but it's also the case that the rise in methane happens almost exactly at the same time as the rise in CO2. It has these other sort of spiky patterns, and we're going to come back to that later. So CO2 and temperature are pretty tightly coupled. For this transition, this is the last transition from a cold period to a warm period. We actually can't do this yet for the older ones because we don't have detailed ice cores like this going back further. That we trade off length for detail. But the evidence that we do have for older transitions would support this conclusion. And we could say a little bit more about why the global temperatures are sort of lagging behind Antarctic temperature. This has to do with something called the bipolar seesaw. There's actually kind of an oscillation in heat between the northern and southern hemispheres that we infer from the ice core records. So when Antarctica starts to warm around 18,000 years ago, it's actually quite cold in the northern hemisphere. And this is probably due to the suppression of deep water formation in the north by freshwater processes. And that in the ice core records, we can see this seesaw between the hemispheres. And because Greenland is cold at this time, the average temperature of the Earth is actually lags behind Antarctica, which is a little bit anomalously warm at this time. So the patterns that we see make a certain amount of sense. But one of the deeper questions I was alluding to is why does CO2 change? Why does this feedback actually happen? What are the mechanisms causing carbon dioxide to be involved in these long-term climate cycles? This is a tough problem, and it's a tough problem because, sort of illustrated by this carbon cycle diagram, the amount of carbon in the atmosphere is relatively small compared to all of the reservoirs of the carbon cycle. And what the atmospheric level really represents is the balance of all the fluxes in and out of the atmosphere. You know, we're asking to understand all of these from the geological record, and it's actually quite a difficult task. So I don't have a firm answer, but one of the things we've been doing is trying to use the ratio of carbon-13 to carbon-12 in atmospheric CO2 to help at least learn more about what the possible mechanisms are. And this is work primarily done by a graduate student with me, Thomas Bosca, who's now at the University of Cambridge. And to do this, people have done this before, but we don't get very much air out of ice. The measurements are a little bit scattered. And so we wanted to move to a technique that required more samples than normal. And that leads to a little bit of a digression about a different kind of ice core sample. If you remember back to my picture of the cartoon of the ice sheet, the old ice is flowing out into the ice margins. And there are places around Antarctica and Greenland where you can actually sample the old ice at the surface. And in that situation, you can get as much as you want, as much as you can carry, as much as NSF will let you take home, which turns out to be a problem sometimes. So what we're talking about here is the Taylor Glacier, which is in the Transantarctic Mountains, located here. Sorry about this, but the map, you have to turn one of these around in your head to get the geography right. But there's a dome here called Taylor Dome, and the ice is flowing into the mountains. It's on this picture, it's over here. And ice flows through the mountains and into Taylor Valley. And this is the dry valleys region. It's very dry, it's very cold. And the mass balance of this glacier is such that it terminates before reaching the ocean. And the old ice from Taylor Dome is actually flowing through the valley and accessible on the glacier's surface. This is an aerial photograph looking towards the center of the ice sheet. So ice is flowing down through the mountains and around and onto the Taylor Glacier. If you can see the banding here, you see some sort of brownish ice. That's actually dusty ice from the glacial period. The flow is such that the old ice is now mostly vertical. The layering is vertical, and age varies across the glacier. And this is about 4 kilometers across here. There's no crevasses. You can camp right out there, collect as much ice as you want. It's a great place to go. For me, it was a nice project because I did my PhD on some glacial deposits way up here in the mountains, 25 years ago. So I got to go back and see the spot again. And this is not the kind of ice where you can just sort of count layers and get the age. We actually have to do a lot of work on the stratigraphy of the ice sheet. We take instruments in the field, measure gases to establish the age of the materials we're working on, and you can see how you can sort of march along and collect ice cores. And by doing that, we can really map out a lot of different time periods that are useful for the work we want to do. And we have a specialized drill that's about this big, so it collects a very large ice core for bringing back large samples for a variety of kinds of studies. So the work that we've been doing is trying to use the carbon-13, carbon-12 ratio of CO2 to learn something about why CO2 changes. It's actually it doesn't give us a complete picture. It does help a little bit. So here's the CO2 record, CO2 rising at the end of the last ice age, and the isotopic composition here. You just think of this as the carbon-13, carbon-12 ratio. For those of you who are isotope geochemists, shows that a decrease in that ratio very abruptly as you go at the beginning of the CO2 rise, and then it sort of stabilizes and bounces around, oscillating between sort of small negative and small positive anomalies. Now, it turns out that this was an obvious thing to do because all carbon cycle geochemists would ask us what the C13 of CO2 should be. It's actually quite hard to interpret because there are a lot of different processes involved. This diagram is some people would call a Keeling plot, but it's actually the output of a carbon cycle model just showing how the ratio and the concentration vary together if you do various kinds of perturbations. And so you get different vectors in this kind of space, and the kinds of processes that would cause this trend are moving downward to the right, gas exchange in the Southern Ocean, land carbon release, changes in the ocean's biological pump. And by trying to, we can start to partition out the change using the isotope records. The problem with this, if you think about it, is that you can add these vectors together so you can get almost any result you want if you have multiple processes involved. So it's necessary to sort of think pretty hard about how to interpret this. But the beginning of the rise is probably due to either changes in ocean biology or upwelling of deep water. And then after that, the isotope ratio is fairly stable, so we think we're seeing a combination of effects like the rising sea surface temperatures and also probably some changes in land carbon. So this was published a couple years ago and certainly still deserves a little more thought. So that's just a little bit about CO2. There's a few additional puzzles. Actually, there's lots of additional puzzles. I thought I'd point out some of the ones that are interesting to me. We don't really know if, for example, the carbon isotopes look the same as they do here in the last transition and all of these earlier transitions. We measure about 1 sample per day. And so getting all of this will take a long time. CO2 is kind of interesting. It reaches levels of about 280 parts per million, 180 at the low end, but then back here, before 400,000 years, the highest concentrations are lower. So there's potentially some kind of long-term pattern. Lots of interesting questions about why we reach these lower limits. Why is the lower limit pretty constant? Why are the upper limits pretty constant? In terms of methane, we're going to talk about that a little bit more, but there have been a lot of interesting questions from atmospheric chemistry modelers about whether the sources of methane really are sufficient to cause all of these changes, or whether we actually have to invoke some changes in atmospheric chemistry in the terms that remove methane from the atmosphere. We tend to interpret this in terms of emissions from wetlands because that has a clear climate connection. But there are other interesting sources of methane, hydrates, fires, permafrost. We're going to talk about that in a minute. And then as you can sort of see, methane variability has a lot more high frequency sort of change than CO2. And that's going to be also a topic we talk about in a minute. One thing, before we talk about methane though, I wanted to bring up one other topic, and that is, can we get older ice than this? And it's something we'd really, really like to do, because if we look at other geological archives of climate, we actually know that Earth's climate really was different prior to about 800,000 years ago. And so this is the isotopic ocean isotope record, which you can interpret as a proxy for the amount of ice on land. And it has these 100,000-year cycles. And these are believed to be driven by the Earth's orbit, although actually why they're roughly 100,000-year spacing in this case is another one of those climate puzzles. But when you go back further, the characteristics of that cyclicity change to 40,000 years, which is the cycle of the Earth's tilt axis. And there's a sense that it was a little bit warmer, or ice volume was a little bit lower. And there's a lot of interest in understanding why the system moves from this kind of behavior to this kind of behavior. One of the explanations that's often thrown out there is perhaps that greenhouse gas levels were higher, overall climate was warmer, ice sheets were smaller and more mobile. But there are a lot of other questions about these time periods. And unfortunately, the oldest ice so far is here. So there's a big international effort spearheaded by this group to try to find a place where we can extend this to 1.5 million years. The goal is to get back to here. And it's very, very difficult because this ice is going to be somewhere near the bottom of the Antarctic ice sheet in a place that's very cold, but hasn't been folded or otherwise lost. And there are only a few places where this might be possible. There's a lot of active exploration to find the right spot. In the meantime, a group at Princeton that I work with, Michael Bender and John Higgins, actually figured out that there's old ice in other places. And this is, has its limits, but it's kind of interesting. This is the Allen Hills, also in the Transantarctic Mountains, another place where ice is flowing towards the edge of the ice sheet and is now ablating at the surface. This is the place where the oldest meteorites that are found on Earth, that is, the meteorites that have been on Earth the longest. And it turns out that there's also very old ice here, sort of trapped in the mountains. And the way we know the age of this ice is because Mike Bender is very clever, and he realized that the decay of potassium-40 in the crust continues to add argon-40 to the atmosphere. And that means that the argon-40 is building up very, very slowly. And if you can measure it precisely enough, you can just date the air. And it works well enough that in this location, we've actually come up with ice that's about 1 million years old, about 1.5 million years old, and then some samples that are about 2 million years old. And what you're seeing here just are the CO2 concentrations from all of those samples and the methane concentrations from all of those samples. So it's a snapshot. And we don't really know the exact time of the snapshot, and we actually don't know how long the snapshot encompasses. But the one observation is that we don't find very low CO2 levels, so that's interesting. And we also don't find any of the very high methane levels that you see in the younger interglacials. So there are a lot of ways to think about what this means. If we are sampling enough of these time periods to adequately characterize them, we would say that we don't find the lowest values of CO2, and perhaps that's related to the fact that temperature might be a little bit warmer. So this is really was sort of serendipitous to find this. We hope that there'll be a lot more ages to go after, and currently waiting to see if we can get funding to go back to this place for more samples and more measurements. The ice is not very deep. It's only about 150 meters below the surface. It's actually not that hard to obtain. Okay, so the last part of this is just to say something about more rapid changes in these gases. And this is something I worked on for quite a while. So now we're sort of going back to a shorter time scale, 60,000 years to 10,000 years. And on the top is the isotopic composition of ice in Greenland. And the 018, 016 ratio of the ice is again, a proxy for temperature. And that you can see the very, very well-known warmings and coolings during the last ice age. They're called Dansgaard-Oeschger events. They take place on time scales of a few decades. The magnitude of the warming is on the order of 10 to 12 degrees for each one of these abrupt changes. And then the end of the ice age is right in here. And these have been known for several decades. Many, many, many studies have gone on about what they represent. It was recognized fairly early on that atmospheric methane has a pattern of variability that matches the Greenland ice temperature record almost exactly. And this green line is a measurement using a laser spectrometer where we take an ice core and melt it slowly and feed the gas into the laser. The number of data points in here is some big number, like 50,000 or something, I don't even know. And this was done by Rachel Rhodes, who was a postdoc with me. This is actually an Antarctic ice core, but the methane variability is almost exactly like the Greenland temperature record. And if you look really closely at these oscillations, which you might, if you're used to looking at climate records, you might think, oh, that's just some kind of noise. You can actually match all of these one for one with the variations in the Greenland isotope. So the coupling is really, really close. The middle here is atmospheric carbon dioxide. You've seen this part already. This is just going back into the ice age. The bottom is, the gray line is the temperature proxy from the waste divide ice core. Now, there's a whole kind of another lecture tied up in this slide which has to do with the timing of temperature change between Greenland and Antarctica and the bipolar seesaw that I alluded to. But I'm going to just focus our attention on these abrupt changes in methane for now, because they're of interest in terms of understanding, how the methane biogeochemistry responds to warming. So we'll zoom in on just one of these events at about 40,000 years ago. For those of you who aren't abrupt climate change aficionados, the HS numbers up here refer to Heinrich stadials, and these are time periods during which there were big ice rafting events in the North Atlantic, which cooled the northern hemisphere and have some impact on the climate system. So if we look in more detail at using this event as an example, Greenland warms abruptly here, and that the mechanism behind this warming is believed to be related to shifts in ocean circulation that change the transport of heat to the high latitudes. The methane concentration changes exactly at the same time, or maybe with a couple of decades lag as the temperature. And I'm not going to talk about the details. We know that phase relationship very, very well. So we have about, in general, 100 to 200 part per billion changes that take a couple of centuries. Another thing that I won't dwell on, but we've been studying recently, is the fact that during the cold periods, there actually are some interesting oscillations in methane as well. And these are associated with changes in atmospheric CO2. These are also very small, but there's something happening in the climate system that shifts CO2 and shifts methane at essentially the same time. The first thing I want to just go into a little bit has to do with this kind of abrupt methane change. When we first started to see these in the ice core record in the 1990s, people started to think a lot about whether they represented some sort of extreme event that we might actually expect to happen in the future. There lots was written about some of the methane reservoirs on Earth that we don't normally think about being involved in the climate system, but hold a lot of carbon. And that's like that includes methane hydrates on the seafloor, and the methane hydrate in the permafrost. So there's a solid methane that's contained in ice structures, and there's a really, really large amount of carbon here compared to what's in the atmosphere. And the observations of abrupt methane change in the ice core record led to thinking about whether it could get out and thinking about whether global warming would actually cause perhaps a very large release of methane. And this kind of thinking continues to show up. So sometimes we see news articles that talk about the methane time bomb and the possibility of large amounts of methane released to the atmosphere. And then other people sort of step in and say, wait a minute, there's not actually a lot of evidence for this. We can look at the question a little bit in the paleo record and try to get a handle on what might have been happening then, and look, for example, for evidence that the carbon from these reservoirs got out during these abrupt warming events. This carbon should be very, very old relative to the surface. And one of the things that I participated in is a project led by Vas Petrenko at University of Rochester, was an effort to make a carbon-14 measurement of methane across one of these events. So this is the methane concentration at the last of the large methane increases at the end of what's called the younger dryas period, fast increase in methane into what we call the pre-boreal time. So this is about 11,600 years ago. What Vas did is he figured out how to get the air out of a ton of ice per sample. So we had to go to that Taylor Glacier location, measure the C14 content of that methane. And what he found was really quite interesting, that there really is very little change in carbon-14 across this time period. In fact, the data plot very, very close to what the atmospheric carbon-14 in CO2 was from the tree ring record. If you had old carbon coming out, you would expect the signal to go down. So there, at least at this time period, not much evidence for old carbon coming out. This also leads to a puzzle, which is why there isn't apparently any old carbon involved in the methane budget. I can leave that one aside, but that's an interesting byproduct of this. We are also working on a few other things. The carbon-13, carbon-12 ratio of methane. I won't dwell on this one, but that's shown in blue on this plot. This is then we're back to my favorite event around 38,000 years ago, and the C13 of methane has some distinct isotopic signatures. For example, biomass burning sources of methane are very different than wetlands, and we don't see much change across this interval. Also suggesting that we're just seeing changes in contemporaneous methane sources rather than some kind of old carbon coming out. And then so the sense is that what we see in the methane record is sort of the contemporaneous cycling of carbon And one of the really interesting things about this is that there is this tight correlation between atmospheric methane, Greenland temperature, and records of changes in hydrology in the tropics and subtropics. One of the more well-known records like that is from a cave in China. This is the isotopic composition of a stalagmite. Full disclosure, that's not China. It's just a picture of a stalagmite. But I think they, I won't say they all look the same. That wouldn't be fair. But this signal is believed to be an indicator of the strength, the overall strength of the Asian monsoon rainfall. And what we see is, and it, you have to dissect it a little more probably to maybe if you haven't looked at these before, but what we see is very strong indication that there's variations in this Asian monsoon signal that match very, very closely with variations in the methane signal. So I think what we're seeing in the abrupt methane data is an indicator of this connection between high latitudes and the tropics. There's a lot of discussion about what the link really is, and mainly focused on the movements of the locations of the main rainfall belts in the tropics. And there's some evidence from climate modeling that when you cool the north, the intertropical convergence zone and rainfall moves southward, and then you warm the north, the opposite happens. And that kind of pattern is also reflected in cave deposits in South America and sort of fits our conception of what's happening with methane. So that's not to say that there isn't a role for Arctic processes in changing the methane budget. I think some of these, part of this increase is probably due to emissions from wetlands in the Arctic that warm. But there's a lot of tropical action associated with this. So that's the end of the methane story. I just wanted to say one more scientific thing. Everything we talk, this is atmospheric CO2 over 500 million years and going a little bit into the future. The age scale changes as we go along here. The ice core record is all in here. These are all geological indicators of carbon dioxide, things like plants, stomata, and isotopes in soils. And this is where we're headed, the IPCC future scenarios. And it may very well be that if we want to understand the future world, we need to go back a fair bit further than the ice core record is going to take us to see what the geologic history is telling us. So that's not intended to be pessimistic, just a scientific point that we are everything we know about atmospheric CO2 so far suggests that we need to head back into the 30, 40 million year range to get to where we might be in the near future. So again, thanks for coming, thanks for listening, and I'll try to take questions. I suspect the answer in the modern environment is that there's not enough CO2 there to matter. There have been suggestions of large hydrate releases into the ocean in the distant past, and that would affect and that's a very interesting observation from the point of view of how good the ocean is at preventing those, and so I would point to that as evidence that it's actually very hard to get hydrate methane into the atmosphere. So that's a consequence of the fact that the oxidation of methane in the atmosphere causes an isotopic fractionation. And when you add methane to the atmosphere if you don't change the isotopic composition but increase the flux, you create a disequilibrium in the isotope ratio because the consumption leaves the atmosphere heavy. And you can model it pretty simply, and it's actually a good sign because it's doing what we think it should. But you have to correct for it if you want to interpret it, and the correction is about what we expect. In principle, yes. I don't, off the top of my head, I don't know the comparison of the timing of sea level, but it would, some of it might fit. I'd have to think about it a little more. The one place where there is a rapid rise in sea level is actually a time when the C13 isn't changing very much. But obviously you're right about the way the signal would go. We sort of have in our mind that terrestrial changes would be fast, and so there would be some timing constraints. But yeah, you can't tell really otherwise. If you mean isotope-enabled models for the water isotopes, we do have those, and they are becoming useful for this sort of thing. If you mean isotope-enabled models for the greenhouse gases, we kind of already have them, but the question is what to do with them. and I think the question is whether they really are capturing the right processes. That's the challenge. And linking ocean circulation change and the carbon cycle on long time scales with an accurate enough, with a detailed enough modeling framework, I think that is actually one of the biggest challenges. Yeah, that is definitely a possibility. So it wouldn't just be, and in fact, that's mostly what's been suggested, that the westerly winds might move. There's some, I think, disagreement among carbon cycle modelers and climate modelers about whether or not it actually is a feasible mechanism.